Oftentimes, graphing is a great tool to identify minima and maxima of a function. So here is a simple function with a graph, and we have a set of points A, B, C, D, R, and S for x values, and we have to determine if they are maximums or minimums. So let's go ahead and look at the largest possible value of this graph, and that value is right here. And the smallest value that we can get for the function is right there. So that is the lowest y value that I can see, and that is the largest y value that I can see. And you have to note that A and S are endpoints. That's where the function ends. So the absolute maximum is at x is equal to S. The absolute minimum is at x is equal to R. But I kind of see a maximum over here, but it only happens about the value C. Maybe if I look at the tiny interval right there, then amongst all those y values, I have a maximum which happens at x is equal to C. So we call that a local maximum at x is equal to C. Using the same logic, we could draw a line on either side of R, and we will see that in that neighborhood, in that tiny interval about R, that value at x is equal to R is a minimum. So that absolute minimum is also a local minimum. Because, it falls in the domain of the function. And we move on to B. B has a dip here, and between two values close to B, that value that we observe at x is equal to B is small. So that is the lowest value on the interval around B. So that would be a local minimum also. And what about points D and A? Well, D is right here. It is not a peak, it is not a dip, and so it's neither a maximum nor a minimum. And if you look at A, it is the same argument, even though it is an endpoint. There are other values that are smaller or larger than what we see at x is equal to A, so neither a max nor a min at x is equal to A. A very, very important thing to note is the absolute max at x is equal to S. So even though we have an absolute max, this cannot be a local maximum. Why, you may ask? Because it is an endpoint. Keep in mind, for us to establish a local maximum, I need to draw an interval around the value that I'm looking at a local maximum for. So at S here, I could draw a line on this side to the left of S, but I can't draw one on the right because the function ends at the point S. So at x equals S, we have an absolute maximum, but we do not have a local maximum because it is an endpoint. Moving on to the next function, we want to find the smallest value that we can think of. Looks like that point at x is equal to a is smaller than that point at x is equal to s. So we have an absolute minimum at x is equal to a. It is smaller than every single value in the domain of the function. Could that be a local minimum? No. Can't be because it is an endpoint. Now what about S? Is there an absolute minimum at S? Absolutely not, because we have the absolute minimum at x is equal to a. It's slightly lower than what we see at x is equal to s. But could there be a local minimum at x equals s? No. The reason being x equals s is an endpoint. So there is no local min or max at x equals s. What about the point x is equal to b? X is equal to b has a value defined, which is right over there. And that particular value on an interval about b is the largest value that we can think of. So that is the local maximum for b. So x is equal to b is a local maximum because if we look at all the values for y in that interval, the largest value happens there. And we do the same for the point C. If I look at that interval of all the values that I see, that particular point at x is equal to c doesn't correspond to a minimum because there is a value smaller than what I see over there. In other words, the values there are less than what you see at x is equal to c. And clearly there is not a maximum because that high value is not included. So x is equal to c is neither a local min or max. Then we move on to d. If we look at x is equal to d, on either side, that is the lowest value on either side of x is equal to d, that point right there is the smallest value for y. So x is equal to d is a local minimum. And lastly, we have a point right here. And that point at x is equal to r is an absolute maximum. Now, is it a local maximum also? Yes. If I draw an interval on either side of R, that particular value that we see at x is equal to R is larger than every single value of y on that interval. So it is also a local maximum. So a graph is of great help when we try to find maximum and minimum. So your calculator is very useful because we get to see the graph first. Then we could use calculus to come up with a better mathematical approach. But to get an initial insight into the problem, it is always great to make use of your calculator. So here we have a function. The domain is 3 all the way up to infinity. If I rewrote this function, I can distribute that 3, 1 over 3, 3x, minus 2 over 3. The 3's would get cancelled. I have x minus 2 over 3. And you should be able to recognize what that function is. That is a linear function. The slope is 1. Y-intercept is negative 2 over 3. Let's graph this. And I'm going to adjust the window, put 3 all the way up to infinity. So I'm just going to leave it at 10. And I'm going to go for minus 2 over 3 as the minimum value. And that is the graph that I get. So on the domain of the function, we start at negative 2 over 3 here, but that's not part of the domain, and it keeps on going. So that would be the point 3. Corresponding value would be f of 3. And it goes all the way up to infinity. Now, does it have an absolute maximum? So since the line is going toward infinity, there is no absolute maximum. Does it have a local maximum? It depends on the interval that we define. So I don't have a specific interval here, so we don't have a local maximum to look at. So, to quantify, because we don't have an interval that is specified. Is there a absolute minimum? So the absolute minimum is the smallest value. So the absolute minimum is at x is equal to 3. So f of 3 would be equal to 3 minus 2 over 3. That would give me 7 over 3. So the absolute minimum is 3, 7 over 3. Now, is that a local minimum? So there is no local minimum at x is equal to 3, because x is equal to 3 is an endpoint. Keep in mind, we can only quantify local extrema if I can draw an interval around the value on which you're trying to find the local extrema. So since 3 is an endpoint, I could look at an interval to the right of 3, but there is nothing to the left. So what do I mean by that? Let's see if it would help. Well, that didn't help. So I am going to put dotted lines up to 3 and solid lines, because that's where the function starts. So to the right of 3 I have an interval, I can form an interval, but to the left of 3 I cannot, so there is no local minimum at x is equal to 3. So here we have another function, which is f of x is equal to 2 over x plus 1. The domain here, 1 is not included, all the way up to 5. 5 is included. So let's go ahead and graph this. I'll have to adjust the window, obviously, because we are getting into fractions. So the y values, I'm just going to set it between 0 and 0.5. And that's the curve we are looking at. When x is 1, f of 1 would be 2 over 1 plus 1, which is 2 over 2, and we end up getting 1. So x is 1, and I have 1. But keep in mind, I am not including 1 because it's not part of the domain. And when x is 5, I have 2 over 5 plus 1, which is 2 over 6, and that would be 1 over 3. And that would give me 0.33, so perhaps I could put it over there. And it's a curve of that sort. So does this function have a local maximum or a minimum or absolute maximum? There is no absolute maximum. Because x is equal to 1 is not included in the domain. Is there an absolute minimum? The absolute minimum occurs at x is equal to 5. However, it is not a local minimum. Why is that? You can only form a local minimum around a particular point if you could have an interval, but there isn't such an interval, so we can't say that there would be a local minimum at x is equal to 5. A simplest way to look at it is because x is equal to 5 is an endpoint. So graphs are quite helpful in getting an insight into extreme values. Here we have an absolute value function. The domain is defined as -5 included, all the way up to +5. So let's go ahead and graph this. We could graph an absolute value by pressing math over to number 1. and 2 times x. I'm going to adjust the window from -5 to 5. And the y values are going to be positive because you can't plug in a negative number in an absolute value function and get a negative number, or for that matter any number. You can't get a negative number when we use an absolute value. So this is going to go from 0 to 10, call it 12, and let's graph. And that's what I would have. The endpoints are included. So that's at 5. That's at -5. And 0. When x is 0, it should be 0. And it is a v-shaped function with a sharp turn. So we can assess and find a maximum if there is one, just by looking at the curve. So now it's interesting here because the lowest value of all possible values, it's obvious, and that happens at x is equal to 0. So x is equal to 0 would correspond to the absolute minimum. Would it correspond to an absolute local minimum? Yes. If I picked a tiny interval about the point 0, the value that I observe at x is equal to 0 is the smallest of all values. So f of 0 is 0, and it is the lowest, so that is also the local minimum. Now, does it have an absolute maximum? Well, the largest value that we can think of is 10. So when I plug in f of 5, I get absolute value of 2 times 5, absolute value of 10, which is 10. When I plug in -5, I get absolute value of 2 times -5, which should be absolute value of -10. I still get 10. So naturally, a function can have 2 absolute maximums, or 2 or more. It could repeat. So here we have an absolute maximum, but are these absolute maximums also local maximums? No. And why is that? Because they are at endpoints. Keep in mind, if we have to find the local maximum or minimum, we need to have an interval about a point. So at 5, I can only form an interval, one-sided interval here on the left. And at -5, I can only form a one-sided interval to the right, because the function ends at -5 and at 5. Okay, moving on to an exponential function. The domain 0 is not included all the way up to 2. So let's adjust the window, 0 up to 2. I guess I'll put 15 and graph. Okay, so that's the graph we have. F of 0 is e raised 2 times 0, which is e raised 0, we get 1. And f of 2 is e raised 2 times 2, which is e raised 4. Now, 0 is not included in the domain. So I'm going to put an open dot and 1. And at 2 I have e raised 4, so which is right over there. And that point is included. So that would be the curve that we have. So does this function have an absolute minimum? No, because the lowest value that we can see for the function is at x is equal to 0, but that particular value is not included, so there is no absolute minimum. But there is an absolute maximum at x is equal to 2, and we have f of 2 equals e raised 4. So as a coordinate pair, that would be 2 comma e raised 4. But is that a local maximum? No. And it is not a local maximum because x is equal to 2 is an endpoint. Here's one with logarithmic functions. So let's make use of the calculator, sketch the graph, and make our interpretations using the graph. So ln of x plus 2 minus 2, and the domain is from minus 2, we're not including minus 2, all the way up to 5, we are including 5. Let's adjust the window, minus 2, all the way up to 5, and graph. I need to have the negative side too. So I get a graph of that sort, and it is going to approach 0. We can zoom this, but it's not going to go anywhere past a positive number. So what happens at x is equal to negative 2? If I plug in negative 2, I have ln of negative 2 plus 2 minus 2, have ln of 0 minus 2, but that is undefined because ln of 0 just drops toward infinity, or excuse me, negative infinity. So at negative 2, I'm going to have something like this, and it is going toward positive 5. So does it have an absolute minimum? No. So there is no absolute minimum. Is there a absolute maximum? but it is not a local maximum. And why would that be? We are going to use the same reasoning as before. X is equal to 5 as an endpoint. So what is f of 5? The ln of 7 minus 2. We get negative 0.05408. So the absolute maximum happens right there, and that value is 5, negative 0.05408. Now we have an interesting trigonometric function, and we know trigonometric functions have periodicity. So this is sine 2x, and I'm going to set the domain from negative 2 pi to 2 pi. Sine doesn't exceed 1. And I end up getting that graph. So try to do this as good as possible. It's not drawn properly, but let me give this another try. Better, I suppose. X, Y, and that's an endpoint. That's an endpoint. And the maximum value here that we see is 1. And the minimum value that we see is negative 1. And when would sine result in a negative value or negative 1? Well, sine x is equal to negative 1 when x is equal to 3 pi over 2. But now we have 2x. So we want sine 2x is equal to negative 1, which would imply that it would end up being negative 1 at 3 pi over 4. We could actually trace this and trace. So there is the first negative 1. It's getting closer to 2.27. And we have another point here, 5.481. So that's another possibility. So at multiples of pi over 2, we are going to have a positive 1 or negative 1. But since we have 2x, we would end up having 2x is equal to 3 pi over 2, and x is equal to 3 pi over 4. So 3 times it comes to be 2.3561, and if I graph and trace it again, so the first negative part happened around 2.5. So we have negative 2 pi there, and that over there would be 3 pi over 4, and that would be positive 2 pi, and that would be 3 pi over 4 plus 2 pi. That would give me 11 pi over 4. So if we move along, we get that point, 11 pi over 4, about 8.6. But that actually goes outside of 2 pi, so that can't be. So let's see. We know sine pi over 2 is 1. But we have sine 2x. This would mean 2x must equal pi over 2 to get 1. So x would be equal to pi over 4. So we can trace and find the other points. So we keep adding pi, I believe, to the numbers to get the other points. So here we would have pi over 4. And we've got to add pi over 4. And graph second window graph. So I'm looking at that point, which is 5.61, and I'm looking at that point, which is 2.27, and looking at that point, which is negative 0.66, and we keep going. So that positive point is negative 2.27, and on the right hand side, that would be 0.8021. So 0.8021, I could write it as 3, or pi over 4. So pi divided by 4, it's about 0.78. So that is the exact value. So you can find all of these points, the peaks and valleys. So we have absolute maximums at all of those points, and we have absolute minimums at those points, and those values are also, Those are an absolute max. Are they? Yes, but these aren't absolute minimums, they are local minimums. Why is that? At the endpoint over there, we get 0. So that would be the absolute minimum. And that here would also be the absolute minimum. So all of the absolute maximum values here are also local max values, because I can draw intervals of this sort around the point, and I could do the same here, I could do the same there, so they are local maximums also, but I can't call those points as absolute minimums. Oh, they are absolute minimums, I am sorry. It's bad math. -1 is actually less than 0. My apologies. So that would be a local what we have. So they are absolute minimums, and they're also local minimums because each of those points we could draw an interval about the value. We could do the same thing here and the same thing there. So I can form intervals about the point, so I could come up with a local minimum. But what about 2 pi and -2 pi? Could those 2 points be local minimums? No, they are endpoints. And obviously, I corrected my mistake. They are not absolute minimums because -1 is less than 0. So that's how you find absolute max, local max, absolute min, and local min for a trigonometric function. Keep in mind the periodicity is quite important, and I showed you where I can start, which is right over here, and then you simply add the period to find the other points, which are right here, there, there, and there. You could also use a calculator to find those values. So now we have, I believe I've repeated a problem here. So I'll simply say refer to previous page. Well, maybe I'll do a different problem. We'll get to that. So now we have cosine t. And the interval is from -pi/2 to pi/2. And let's change and that's what we end up getting, and it's a nice little curve. So that point right here is the maximum of all points, and it is part of the domain. So that is the absolute maximum, and it is also a local maximum because we can draw an interval around that point on both sides, and the absolute maximum would be the largest on that interval. So it's a local maximum also, so at x is equal to 0, t, and f of t is cosine 0. Cosine 0 is 1. Now, what is the absolute minimum? The absolute minimum is 0. Happens there. Happens there as well. But are the absolute minimums local minimums? No, because they are endpoints. Let me go ahead and change this problem a bit. Maybe I will change this problem to f of x equals cosine 4x 0 less than or equal to x less than pi. Okay, so let's go back here. Cosine 4x and adjust the window 0 to pi, and the domain here 0 is included, pi is not, and let's graph it. And that's what we get. So we have so that point we can't include, so I'm going to put an open dot there. So that's at pi, so 0. And cosine 0 would be 0, and we know that we get a negative 1 when x is pi. So we have 4 pi, or 4x is equal to pi. This would imply x would be pi over 4. So that point right there would be pi over 4. And 0, and we have to add the period, and we would get at 2 pi to be 1 again, and add a period of can't be 2 pi, I'm sorry, 2 pi over 4, which would be pi over 2. Is it pi over 4 and 0? Next one would be at 2 pi. It's pi over 2. And the next one would be minus 1 at 3 pi, so that would be 3 pi over 4, and so forth. So I'm just plugging the values in for 4x, so I know cosine would become 1 at 2 pi. So I'm setting 4x is equal to 2 pi, x would be 2 pi over 4, which would give me pi over 2. The next time cosine would become negative 1 would be when it is equal to 3 pi and so forth. So I'm using the properties of periodicity to determine the next values, for the cosine peaks, +1 and -1. So I have, oops, -1 there. So y, x. So what are the maximums? So 0 is included. So absolute maximum. Absolute maximum. That is not an absolute maximum. You can't include that because that's an open point. Absolute minimum. Absolute minimum. Could those be local minimums? Absolutely. So local mins. These are local max as well, because I can draw an interval about those points, but I just cannot include this point, unlike the sine 2x problem, cannot be included because x is equal to pi is not in the domain. Good.